Well, hello everyone and welcome to this next lecture on Python Power Electronics, and in this lecture I'm going to talk about how we can have multiple control files in the same simulation and how we can connect them together. So as before, I will start off with the Python Power Electronics website and go down to the download section, go to papers, and as usual have this paper control structure ready. So this is just for your ready reference, and in this case I have already spoken about most of them. I've spoken about input, static variable, variable storage, and time event. Now, in the lecture related to variable storage, I had spoken about how variable storage can be used for saving control variables into the output data file so that you can plot them later. But variable storage also has another purpose, and that's what I'm going to describe in this lecture. So let's go over to this command line and let's launch the circuit simulator. So I am now at my virtual environment. Let me start off and just to check whether I have the right Python version. Yes, I do. So all these commands are very standard commands. If you need any help, just go to any of the previous lectures, or just check out the lecture on installing Python in the circuit simulator in Linux or Windows. It's the same both ways, because in both cases I'm using virtual environments. So the circuit simulator is running. All I have to do is go over to my web browser and launch the simulator. The website is already stored. Go to simulation library. So far there is only one simulation. At a later date there may be more simulations, but for now there's only one. So I load the simulation, save, back to main page, add circuit file. Nothing to do, but remember, as always, even if you're not changing anything, if you're launching the simulator launching the server and starting the simulator, you must process the circuit schematics. Nothing will happen without that, because process circuit schematics launches the circuit objects into your RAM. That's what is needed to actually run the simulator. Edit circuit parameters, nothing to do, just go back. Now we are ready. So now I will go into edit control. So before that, let me talk about something here. So now I have this file switch control.py, which is what I've been using right from the beginning. I am going to now create another control file. Let me call this control2, control file 2.py. Not a very imaginative name, but that's okay for now. We're just trying it out. So I'm just leaving the empty file, nothing else. What I'm going to do is I'm going to go back and I'm going to add this file. So what I'm going to do, I'm going to choose this file, it is in diode rectifier, and it is control file 2. So let me open this and let me just say sample second control file. Okay, nothing else. Save this file. Now I'm going to not configure the control. I'm not going to do anything. Why? Because I want to show you what happens without any of these. Okay, so let's go back to back page. I'm going to go view output and I'm going to run this simulation. Alright, now it's weird here me doing this, but I'm going to show you why I'm doing it. Now that the simulator is running, I'm going to go and check out what this underscore control file does. So first there is the original file, that is switch control.py results in switch control underscore function, which is what it was before. And let's scroll down and you see now there's another function. Alright, this file is called control file 2 underscore func. Alright, as usual, remember, whatever is the name of your file, that is control file 2, whatever is your file x.py, the function is called x underscore func and the code is embedded inside. Now what's very interesting is, check out what else is happening. I have not defined anything, so there is literally no code. There is all this is boilerplate code inserted by the circuit simulator. My file is empty, absolutely empty. All this is coming in. Now let's see what's happening here. You see these variables here? Let's go back here and check what's happening. These were the variables which were declared in the previous simulation, in the previous control file. All right, these were not variables that were declared in this one. So what's going on? Let me go back here and show you what's happening. I'm going to stop this and I'm going to go back to main page. Edit control. Let's go to this one because this is all that has anything. And let's go back to the variable storage elements. So there is store var1, store var2, store var3, store var4. Okay? I use them for different purposes, and they appear here. Okay, this, what do you call, the order is different, but the order doesn't matter because they are actually stored in a dictionary inside the simulator, which is why it's like this. What matters is store var4 is extracted from an internal circuit simulator variable. All right, okay, you don't have to worry about this, but it's extracted and it is stored back again at the end of the function. But you see what's happening here, exactly the same thing is happening in the other function. I didn't do this. There is, remember, this other function is empty. I have not done any configuration. Look at this. No inputs, no outputs, no time events, no variable storage elements. So what's going on? What is going on is this. When you define a variable storage element, any variable storage element in a circuit simulator, in a control file, this variable storage element is available in all control functions. It becomes a global variable. All right, it becomes a global variable. Why did I actually do this? There are two reasons. One, when you want a circuit simulator or when you want a control function to produce an output. Now remember this, an input, if I want to add an input, let's say I'm going to try to add an input here. I want to add an input, control add, I'm going to add this input. What are my choices? My choices are only the meters. All right, an input to a control function can only be from a meter. Similarly, okay, I have to put something, save this input, and I will just delete it because you can't leave it, it's an error. And I'm going to add this, and I'm going to add a control output. What is my control output? There is only the switch. So what I'm trying to say is, in this circuit simulator, if for a control function, the input can be only from a meter, the output can be only to a controllable element. But in reality, in usual simulations, we like to break our control function up into several different blocks, right? That's usual, that's normal. In that case, the input to a function cannot just be from a meter. Similarly, the output cannot only be to a control element. The input has to be sometimes also from another control function. Similarly, the output also has to go to another control function. So that's the problem. Now how do I do this? Let me just give some random variable, save this output, and let's delete it. So I'm going back to the empty state. There is absolutely nothing. And the way we achieve this is using variable storage elements. When you want to exchange variables between control functions, you use the variable storage element, because a variable storage element is available in every control function. So once you define it in any one control function, it's available in all others. Now I'm going to show you how this works. Let me just close this file. Let's use already the existing ones. Let's go back, or let's just define another one. So let me go back, let me configure a control file here, and let me call this add variable storage, and I shall call this input from switch control. You can name it anything you want, that's not a problem. I'm going to just give it a you must give it initial value. Initial value need not be anything important. Now in this case, the actual purpose of this control, this particular variable storage element, is not to plot. I'm not interested in plotting this. Now if you want, you can also plot it. Yes, you can also do this. But if I say no, it's perfectly okay. Alright, now I'm going to show you how this happens. I'm going to save this, and I'm going to add another variable storage element, and I will call this store var 5. I'm going to say 0 is the initial value, and I'm going to say yes. So I am declaring two variable storage elements. The first one I am not writing to the output data file, so you cannot plot this, and I'll show you how this happens. And in the second one, I'm saying this is a variable storage element which is only for the purpose of storing it. Alright, so I'm saying yes here, storage state is yes. When I say yes, it means it's plotted in the output data file. So I'm going to click on this. So now that we are done, I'm going to go back. Well, actually I shouldn't go back, let me just check it out. And I'm going to edit my control file. So name of this, let me just copy this name, because it's a long one, I don't want to make a syntax error. And let me say input here. Alright, I am now, or rather the way it would work, how do you want to do this? For example, this variable is available in all files. Okay, so I can edit it anywhere, and the best part is I can also edit it somewhere else. So let me go here to this one, and this variable, like I said, it's a global variable. Once you declare it in a control function, it is available in every control function. So it's also available here. I have declared it here. All right, that variable storage element is here to this function, but it's also available here because that's how it's defined. So let me do this, and let me call iSource1 divided by 2. Okay, so what am I doing? I am saying that this local variable here, this is a local variable, I'm sampling it. Okay, I'm sampling it within this time period. I am now setting this value to a global variable. All right, this variable which is now being assigned this value is also available here. Okay, so let me do that. Let me go to X range, let me do this, and let me give it some value. I don't want to 1 point, let's say 1.2. I just want to plot these together. Now let me now use this last one, that is store var 5. Remember, this is a global variable which is not plotted in the output data file. This is a global variable which is plotted in the output data file. So let me now assign this value to X. So what am I doing? I have this local variable X. I am assigning this value X from a global variable. This global variable is actually defined here. So what am I doing? I am passing variables between control files. I am passing this value iSource divided by 2 to this file. That's essentially what I'm doing. So X contains this manipulated value. This is how I'm controlling the file. And then what am I doing? I'm plotting it. You can do anything else you want. You can run a PI controller on this. You can have another time series. So I'll show you all that. So let me just go. Now that we've done this, let me go back and plot this. Run the simulation and plot it. So I'm going to run this. Simulation is running. As always, go to the command line and check if there's an error. No, there is no error, so we are okay. So now that the error is gone, let me go and plot these variables. So let me add a plot. Let's call this var store 5. Now, when you are actually using your circuit simulator, I would suggest that you name your plots a little more elaborately. Here is just an example, but for the sake of clarity and you're able to use the circuit simulator, always use names which are a little more obvious. So now I'm going to add a waveform. Now the first thing I want to do is I want to check what is there. So you see what's happening here. I have store var 1, 2, 3, 4, 5. There is another global variable. You know what that variable is? Let's go back here and check. This is also a global variable. This is also variable store element. So where did it go? It's not there. Why? Because I set the storage status to no. I said do not plot this in the output data file. So therefore it's not in the output data file. So let me just plot these values. Let me say this is is. Let me plot another waveform. Let me now plot, let me go back and check. I am plotting store var4, so let me plot store var4 and store var5. So I'll call this var4, and eventually I will call var5. So we're ready to go. Let me save this plot and let me plot it. So the plot is done. Let me go here. Let me go to my file, and there's store var5. So okay, now I'll have to zoom in. Okay, let me just pick out some of them. 0.02 to 0.0. I'm just plotting in a smaller range. I'll just make it 4, and let me plot this. That's surprising. I don't know why I didn't plot 0.02 to 0.04. Let me just go check. Probably I entered the wrong range. That probably happened. When you enter a wrong range, it will plot the entire output data file. Let me check again. Yes, I think that was a mistake. I just plotted the wrong range. So you see what's happening here. I have now, the blue line is the source current. All right. Now I am now sampling this source current. You see var4 has been defined in this file. All right, and it is sampled at 100 microsecond. Now I am also assigning this global variable to half of the source current. You see what I'm saying? So it's like half of this source current. Now in this other file, I am now multiplying again by 1.2 just for the sake of it. All right, I don't have to do that, but I could, and I'm plotting this file. So therefore you see what's happening. This file is sampled exactly as it is. All right, let's do another one. Let's zoom in between 0.025 and 0.03. Let's make it even more clear. So 0.025, 0.03. I would strongly suggest that you try it out on your own, because that's the best way to actually learn this, but I'm just trying to make it as clear as possible. So you see the sample, the orange line is the sampled source current, and you see the green line, which is in the second control file, is mirroring the sample but is scaled by that factor, that is divide by 2 multiplied by 1.2. So, and I'll show you how you can actually even change the scale. Let's do that. So I'm going to go back and stop this, and as I said, every control file is independent, so you can do whatever control you want, you can define anything you want, no problem. So let's go back and define some more variables there. Edit control, configure control. So let me go and add a time event variable. Now there's something to be said. The only thing is, the only global variables are the variable storage element. Variable storage elements are global variables. All right, so they have to be unique. All right, you cannot have two variables of the same name in two different control files. That's illegal. But you can have all other variables to be identical, no problem. So you can have the same. I can have t control 1 here too. All right, t control 1 was in the previous one. I can also have t control 1 here, no problem. Let's do that. Save this time event, and let me also add another control static variable. Let me say sample current. All right, so I have defined a static variable, defined a time event variable. Now let's go and use that here. So the first thing I'm going to do is I'm going to say if t clock is greater than t control 1. All right, what am I going to do? I am going to say sample current is equal to x. And as I said, always never forget this. When you define a time event variable, always update it. Now here I have defined 1 point e raised to minus 4. Let me define something else here just to show you that it's possible. So I am going to sample this at 200 microseconds, and let me know I am going to store the sampled current rather than the actual variable. All right, just to show you what can be done, how it works. Back to control main. Let me run this simulation. So like I said, this way you can actually have independent controls at independent time events, running all of them separately. The circuit simulator will guarantee that every control function is run when the time event occurs. That's what is important, and that's what I'm going to show you in this plot. So let's plot it. So you see here, it's pretty obvious. The time event here, the current is scaled. All right, the green current is scaled. See, the blue current is the actual source current, instantaneous value. The orange value is the sampled current. It just follows, it's a stepped waveform. The green current is the current which is transferred from the first input file to the second input file and is sampled at a different rate. You see here, okay, let me zoom in again. 0.002 to 0.004. And let me plot this. Let me go back to the previous thing. Let me just check. And it's obvious. You see here, now it's very obvious, the step change. You see the step here, the orange one and the green one. The step size is clearly double. You see, two of these steps are equivalent to, two orange steps are equivalent to one green step. Why? Because the second control file is sampled at 200 microseconds. The first control file is sampled at 100 microseconds. And this first sampled current is fed to the second control file where it is sampled at a different rate. You see, this is the flexibility of the circuit simulator. You can have different sampling instants, you can have different control variables, you can do whatever you want. In this case, so what you could do is you can run a PI control on the first one, you can run another PI control on the second one, so you can have multi-rate control. Right? You can have an inner fast control, you can now have an outer slower control. You can do these things. That's the advantage. So anyway, this is pretty much all there is to discuss, and I think I will wind up this lecture series, like this lecture here. There is one last lecture in this series, and that is for the output. I have covered everything else. I covered input, static variable, variable storage, time event. I have also covered how you can have multiple control files. So now the last is, how do you actually control the output variable? Because so far all the control is internal to the control functions. We have to get the control variable out to the controlled element, and the controlled element is a switch. So how do we do that? That will be in the next lecture. So for now, I'll end this lecture again. Thank you so much for watching. If you have any doubts, feel free to message me either on Facebook or on Gmail or anything else. And so look forward to creating the next lecture. As before, I have not released any of the control files, but I would suggest that if you really want to recreate this, try playing around this all over again. I think these are pretty visible in the actual videos. Rather than actually providing this open source, I would encourage you to create these same files on your own if you want to learn the circuit simulator. So anyway, I shall get back to you soon with the next lecture. I think it will be soon because it's a weekend. And thank you again for watching. See you soon. Goodbye for now.